and 200 MeV is the natural scale for strong interaction physics. Okay, so what is the constituent of matter at that density is one of the important questions to ask for. And is it there? I mean, of course, neutron stars are there, but is there a dark matter inside it, or it is just neutrons, or what it is, or any exotic things are there? So we can study or get some information about it.
Next slide. How do I go to the next?
Down. Yeah, so this is what I planned. I gave him kind of introduction, but I will elaborate a little more. And then I will discuss a little bit about hadron quark phase transition. Hadron means it is like proton, neutron, bound states of quarks, pions. Quark anti-quark pair like a meson, which example is a pion, and three quarks like a proton or neutron. Okay. In general, it's called a baryon. Okay. So when I'm talking about hadron quark or neutron star, the hybrid star, naturally I should have a description for how does neutrons and how in the theory I am describing the hadrons or the neutron or proton, and how I am describing the quarks. Okay? Then only I can compare the two and then try to find out whether there is a phase transition or not. So there are interesting models for that for nuclear matter, or the hadronic matter. It's called a relativistic mean field model. And to study neutron stars, one of the important things that goes in the calculation is called equation of state, or EOS, what I have written. What is EOS? How does the pressure is dependent on the energy density. Okay? That relation is little non-trivial. It varies from theory to theory. So there are many people having different models and giving many equation of state. And which is the correct theory? And that you can put which is the correct theory by looking at observations. And these neutron star observations restricts the equation of state, which is allowed, which is not allowed, and those kind of things. Okay? So there is the mean field model I will choose for hadronic matter. Profulo is an expert on that. And then Nambu-Jonas-Lasinio model. This was a model for quark matter. Actually, Nambu and Jonas-Lasinio, Nambu got the Nobel Prize for this thing, and they had a model for nuclear interactions based on how do the nucleons get ions. So that model is, they did it for nucleons, but then later it was generalized to quarks. And that model I use for quark matter. I discussed phase transition. Phase transition is that you all know about how different phases exist. Water, ice, steam. And it turns out that actually water phase diagram is much more complicated. You guys know about this common base. But the point is, you can discuss different phases by calculating what is called as thermodynamic potential or free energy or the negative of pressure. So the one which is higher pressure is the preferred phase. Just like in any calculation, you say for this system what is the energy, and if you find out some other configuration which is lower energy, it will go there. One with higher energy is unstable, it will go lower energy. At finite temperature or finite density, like the system there, in thermodynamics, it is not the energy, but it is the thermodynamic potential, or sometimes it is called the free energy. So that you will compare, and whichever has lower free energy or lower thermodynamic potential, this is given by Gibbs, and that is the preferred phase. So you calculate the pressure for magnetic matter, for neutron matter, you calculate pressure for quark matter, and for some parameter you try to see which has lower free energy and at what density. Whichever has, you expect that if density is very high, it might go to quark matter phase, or temperature is very high, it can go to quark matter phase. But you should be able to compare, so you should be able to calculate what is the free energy in these two models, and then decide which is thermodynamically a stable phase. So that I will do, and then I will discuss a little bit about non-radial oscillations in neutron stars, and finally I will conclude. And there I will discuss about that if the neutron star has a quark matter core, its oscillation modes are different if it has it's not a hybrid star but a canonical neutron star, only neutron matter. The frequencies will be very different, different range, and that can probably be detected in the gravitational wave detectors. So I will. So that is my punchline. That if there is a quark matter, there will be certain modes which is characteristic of a quark matter core in the neutron star. So that distinguishes. That's what I mean by unmasking hybrid stars.
Down, right? Yes.
Okay, so this is a sketch of the phase diagram of strong interaction. This is a schematic phase, and what this is essentially is plotted in the plane of temperature in one axis and density is another axis. This density is the particle number density. That is how many particles are there. Actually, it is not particle. It is particle minus antiparticle, because at high temperature you can produce particles and antiparticle. It is the finite number density. Particle minus antiparticle is actually the number densities. And that is plotted in x-axis and temperature is at y-axis. And as I said, at high temperature or high density, the system is in terms of, described in terms of quarks and gluons, that constituents. And if you go from here very high temperature and you go along this axis, at around temperatures about MeV, a few hundred MeV, that is 1 MeV is 10 to the power 11 degree Kelvin. 10 to the power 11 degree Kelvin. So this the quark matter phase goes to the hadronic phase, or ground states of quarks come up around temperatures of 160 MeV. That is the theory says, that is what is known also from experience. And this I have told about early universe, because as you know, the universe started with a Big Bang. That is the theory we know. And after Big Bang, it was like a point and then started expanding. As it expands, it cools. And a few microseconds, few tens of microseconds after the Big Bang, the temperature was about 100 MeV, that is a good estimate, 150 MeV. When this phase transition might have occurred, that is what is the expectation is from ab initio calculations. And actually it is not a phase transition, it is a crossover transition. I will tell you what is the difference between a crossover and a phase transition. And then, so this is the path the universe took. It's almost zero variant density. that is, here the number of baryons and antibaryons were same to start with. There is no net baryon density. Why we only see baryons now is an interesting subject in itself. It's a phenomenon called baryogenesis that I won't talk about it. Again, we'll take few lectures. But the point is, we see only baryons now, and it is at zero density, zero net baryon density. And this axis, this is the finite nucleus. If I call it 1 in some unit, actually this is about 0.16 nucleons per Fermi cube. That is the nuclear matter density. Here is the nuclei. There is a small 10 MeV. The nuclei is thought to be actually a liquid, and there is a liquid gas phase transition about 10-50 MeV. I won't go into that. But at small temperatures, if I go about 4 to 5 times nuclear matter density, that is supposed to be the neutron star density. And if you go very high, that can be, I mean, there is a band here because it's not a sharp transition. I mean, it is not known clearly. There is a lot of uncertainty theoretically. And if you go very, very high, you expect it to be quarks. And the quarks apparently should be in a superconducting phase called as color superconductor. They are like your usual superconductor as electron pair up, BCS theory, spin up, spin down, then pair up to like superconductors. So here, instead of the phonon-induced interaction, it is the fundamental Q-city interaction gives rise to some attractive force, which they pair up. So it is the pairing mechanism is the color interaction. So the name color superconductor. So the idea is, okay, what we know about the phase diagram concretely is about a zero baryon density. That it is a crossover transition. At finite density, what happens? How it is done? Whether it is a first order transition, second order transition, we don't know. So a lot of uncertainty is there in this finite density regime. And these are also experimentally accessible zero baryon density, and it was explored in the heavy ion collision experiments. I think Vedanta will talk tomorrow. And so this was a crossover transition, and many models they said this is a fast order transition. And so if it is a fast order here and a second order or a crossover transition here, in this phase diagram as you go up, there should be some point where this fast order transition becomes a second order or a crossover transition. So that is called a critical point. And most of the experimental program in heavy ion physics, where they essentially collide two heavy ions of very high energy that thermalize, and they have a temperature which is what was there in the 10 microseconds after the Big Bang, that kind of temperature that is created in the laboratory. And searching for this critical point is one of the programs, and possibly infer something about the matter in what is converging, what is merging in merger of neutron star or black hole. And that signature you can see. So that has become very important in the context of neutron star. Yeah. So they are, as I said, they are very interesting objects to study the area of matter at extreme densities. Extreme meaning Q times nuclear matter density, like 0.16 nucleus per Fermi cube or 10 to the power 14 grams per cc. This is the nuclear matter density. So Q times that is the density inside neutron stars. And there have been observations that neutron stars, also the maximum mass is of the order of 2 solar masses. There are some observations. These are the things. This is a challenge. I mean, you might say that I have an equation of state of neutron star. I can nuclear matter. I can generalize it, get an equation of state, and I should have a star. And it turns out that you get stars of maximum mass about 1.5, 1.6 kind of thing. It's very difficult to get a high mass neutron star, and people try to put in hyperons, the higher mass variance into it and make it more complicated. If you put hyperons, there will be the mass will reduce rather than increase. So this was a challenge. And unless you have a very strict equation of state by some means or the other, it doesn't give this 2 solar mass neutron star. But it is a challenge because it is observed. Then there are these Virgo and LIGO collaborations which observe this binary neutron star merger. This is the event. This is a good observational window on the compact star. What they observe is the gravitational wave from this merger, and as the 2 stars try to collapse, try to merge, the gravitational field of one deforms the gravitational field of the other. There are some tidal waves that come up. And this deformability is related to the gravity field, Eij. The proportionality constant is the powerful deformability. So this is lambda is the proportionality constant. Or if you take appropriate dimensionless, you try to match it, and it is proportional to some constant times r by m to the power 5. Very sensitive on the mass and radius of this neutron star. This are what is known as compactness. Radius and mass. So how compact it is. So that kind of a feeling it gives. It is proportional to the 5th power. And the phase difference between this gravitational wave, the delta phi, that they observe, is proportional to this parameter lambda. So this delta phi, the phase difference, is a very sensitive function of mass and radius. It varies as m by r to the power minus pi, or r by m to the power pi. And this mass and radius depends upon what equation of state you take for the structure of the neutron star. So there are thousands and thousands of equations of states, and you have many, arbitrary. So how do you know? So you calculate this quantity, lambda. It should come over the observation range, and that has rejected many equations. So it confines. You can reject many equations of state out of this measurement. And however, so tidal deformability constraints equation of state at high density. It is possible, though not conclusive, that these 2 stars which are merging could be hybrid stars, either both or at least one of them. But it turns out that there have been calculations which show that even if it is a hybrid star, it can be within that limit. There are papers here by Mandi, Alford, and these people. A hybrid star with a quark matter core is indistinguishable from a canonical neutron star based on current observational status. So this was the name given Alford as a masquerade problem, and someone will say how to unveil the veil. That is the problem. Whether you cannot do that from the tidal deformation data, because even if it is hybrid star, you can distinguish. It can be within that limit. Even if it is neutron star, it can be within that limit. Although this limit is very very, very sensitive, m by r to the power 5. So, there is, it has been suggested that there are some oscillation modes of neutron star can have possibility of providing compositional information. What kind of matter is inside the star, whether there is a hyperon force. Hyperons are cousins of neutron proton. They have also strange quark in it, and it's strange variance. Even a quark core or mixed phase with quark and hadronic matter, you can even or ionic matter. There are many possibilities in neutron matter at high density. So, as I said, the mass and radius of a star depends upon the equation of state. That is P versus epsilon, the relation between pressure and energy density. Okay. But this oscillation turns out that it is not only depend upon P and epsilon relation, but also this oscillation depends upon derivative of pressure with respect to energy density. Okay. That is called speed of sound. dp by d epsilon is called square of speed of sound. Okay. So this dp by d epsilon is actually very, very sensitive thing in space condition. There can be a discontinuity and all that. So that is the basis of this calculation. So the core of neutron star in principle support various phases of QCD matter, and there are various, as I said, quark matter in the superconducting phase, but it is only done to validate much high density. The other thing to do, a reliable calculation is using lattice QCD, but that is limited to very low barium density, and realistic density on the other hand are not asymptotically high, this 40 times ns, or it's 4 to 5 times, and so it is not too. So there is some uncertainties here. So we try to look into this structure of neutron star, giving a concrete example. You take nuclear equation of state and you take quark matter equation of state, do a phase transition structure, and see what is happening. So this is just briefly summarize about hadronic equation of state, which is called a Waleska's mean field model. Essentially, it is you have nucleons, that is neutron proton, they interact by exchanging scalar mesons or vector mesons. Mesons, as I said, are quark antiproton states. Okay. So it is known that if two fermions are exchanging a scalar meson, scalar particle, it is an attractive interaction. And it is a vector particle exchange, it is a repulsive interaction. Okay? So you can choose the coupling such that appropriates mixture of scalar and vector, so that you have the saturation property of nuclear matter. That is, the binding energy for nucleons should be minimum at the nuclear matter density, that is 0.16 nucleus per atomic cube. So this is the essential of this mean field model. You have a scalar interaction, you have a vector interaction, and you can later on put in different kinds of things to describe other properties of nuclear matter. 5-2, 5-4 term. This is a vector interaction part. This is the vector parallel of at mu, and this is the m rho square Romeo and this square Romeo. And if neutron proton number is not the same, that you can distinguish by having an iso vector scalar exchange. So once you have it, you don't include rho and omega. Yeah, V is rho and no, rho omega coupling. No, here it is not there. Or it is there, I don't know. I think here we have not taken. Yeah. Okay, once you have it, you can calculate in a mean field level, you solve the Lagrange equation of motion. You have the Lagrangian, so you know what is Lagrangian equation of motion. And you solve it at the mean field level, which means that you treat the field expectation as a constant and treat the nuclear fields as quantum fields, and you can calculate the energy density and pressure. So it is some expression. You can get. This is how it is, and you can calculate pressure and energy density. So these are some of the model parameters. Yeah, NLP parameters. So that was the hadronic part, and this is the Nabu-Jonas Lassinian for quark matter. It's a two-flavor one. It's a four Fermi type, four particles, four quark operators are here. This is an interesting model which gives the mass to the nucleons. You must have heard about Higgs particle. Higgs particle gives masses to all of us. That is what they say. But Higgs particle doesn't give all the masses. In fact, mass of the proton is about 1 GeV, that is 1000 MeV, out of which 3 quarks, they are massive of about 5 MeV mass. So this 5 MeV comes from Higgs mechanism. So 15 MeV comes from Higgs mechanism. From where do we get about 300 MeV? Because 3 quarks make 1000 MeV. So each quark should have 300 MeV. 15 MeV comes from Higgs. From where do we get this 1000? Rest of the mass? It is the strong interaction. QCD gives you that. Okay. So this phenomena of generating mass, namely technically what is known as chiral symmetric breaking in QCD. So this model describes it very well. So this is how this model is used. The M here is about 5 MeV, but the mass that you get, the so-called constituent mass, comes out of it about 300 MeV, and hence the proton mass is about 1 GeV, 3 times. Okay, so you will try to calculate again the similarly pressure and energy density. So that is what is done. It has to be done in a self-consistent manner. The constituent mass that I said is M, which is sum of this little m, and this is from the interaction. So not only that, you also have to put the conditions inside the neutron stars. Neutron stars are charged neutron. They don't have a charge, electric charge. Okay, so that condition you should put in the beta equilibrium and charge neutrality condition. So that essentially sets you this is the charge neutrality condition, and this is the beta equilibrium condition. Anyway, let me not go into it. The only part I want to emphasize is that you have to impose this charge neutrality condition, and so the pressure of spark phase is written like this, and you have to put in some electrons to make it charge neutral also. These are the parameters. It's not very important. So then I have to know which phase has higher pressure or lower thermodynamic potential. Okay, that is the Gibbs criterion. It says that for a given temperature and chemical potential is a proxy for density. Okay, and it says that for a given temperature and chemical potential, for the phase transition to occur, both the phases will have the same pressure, same thermodynamic potential. Okay. And that phase is preferred, which is higher pressure, or lower thermodynamic potential. Okay. It is the same thing as energy principle that we have learned generalized to thermodynamics. Okay. So you can have two kinds of ways it can be considered. One is that here there are two chemical potentials are like Lagrange parameter or the constraint that you put so that will correspond to some conserved quantity. The conserved quantity that is used here is that the baryon number or the proton number is conserved and electric charge is conserved. So you have to keep putting two corresponding chemical potential. As I said, for each conserved quantity you put in a chemical potential. So what you have a electron chemical potential and there is a baryon chemical potential, neutron chemical potential, proton chemical potential. Okay. The condition is that the both should be the same. So you can have, there are two ways here. If there are two kinds of matter, of hadronic matter or quark matter, you can mix the charge neutral quantity of hadronic matter or electric charge neutral quantity of quark matter and then compare the pressure. Okay. Now, if you want local charge neutrality, then when you put in the charge neutrality condition for each kind of matter, then the mu p becomes a function of mu b. So then you have to put in this condition. Effectively, mu b is known. Pressure is actually a function of mu b and mu p. Charge neutrality tells me this relation, so it becomes this. So you have a charge neutral hadronic matter, you have a charge neutral quark matter, and you are comparing pressure. This is called the Maxwell construction. There is something called the Gibbs construction, in which you can have, for example, a positively charged hadronic matter, and you can have a negatively charged quark matter, with the total matter being charge neutral. Okay, so that is called the Gibbs construction, and that is what we try to do here. Which is preferable depends upon the surface tension between the two phases, but that is something is not known. So as an example, we did with Gibbs construction. So here it is, I just put, here it is neutron chemical potential mu b and this is mu e. Pressure, the green is for the mean field level, mean field. This will be the surface because it is a two-dimensional thing. Pressure is a function of mu b and mu e. And this purple is for the quark matter. So these two surfaces cross, we satisfy along this line. This satisfies the condition, Gibbs condition, that pressure in hadronic phase as a function of mu b mu e is same as pressure of quark phase as a function of mu b mu e. So this line tells that. The two surfaces will cross along the line. Now you have to also impose that this is charge neutral. So along this line, there is certain area which is chosen. Along that dashed white line, it is not only pressure between the two phases are same, but they are also globally charge neutral. Okay, that's the fraction of hadronic matter might have one charge. The fraction of the quark matter will have the other charge. But in total, it will be charge neutral. And below this point is the hadronic phase, and above this point is the pure quark matter phase. In between, a fraction of quark matter and a fraction of hadronic matter. And it turns out that the mixed phase starts from this baryon density was 3 times nuclear matter density and ends at about 5 times nuclear matter density. This is okay, so you have a structure. If you have very large density, extremely large density, you will have a quark phase. If it is low density, it is a hadronic phase. But if it is moderate density, you can have a fraction of matter in hadronic matter and a fraction in quark matter. And you can have a corresponding equation of state also. This is what I have written down. This is the hadronic phase. This is mixed phase, and then this quark matter phase. Okay. And this is the fraction that I was telling about. Fraction of quark matter is plotted here. So beyond 2.4 or something, the mixed phase starts, and the fraction of quark matter increases until it becomes about 5 times nuclear matter density. It becomes 1, and above 1 it is pure quark matter. This just gives you an idea, nothing much is there, and you can calculate how many, what kind of particles are there in that mixed phase. So you use this, once equation of state is there, you try to solve what is the mass and radius of the neutron star. The basic physics is, this is done in long time back by Tolman, Oppenheimer and Volta. The basic physics idea is that you have a lump of matter, you are trying to compress it, the formulas you will repair. And this repulsion is kind of restrict or opposed by the gravitational attraction. So there will be a uniform, there will be equilibrium position. So that will define the star. Okay. This is essentially the physics of it. And you write down nice, complicated, general relativistic equation in a proper metric. This turns out to be, this is the metric you take, and these are this is the differential equation for pressure, and this is the differential equation for mass enclosed in a radius of r, and this is the metric function, this phi r. So these three equations, these are essentially three coupled equations with boundary conditions you can solve. By taking this kind of a boundary condition, the mass enclosed at the center is 0, the radius is defined by pressure at capital R is 0 because there is nothing, beyond R there is nothing, no pressure. And this is the limit of this metric function, 1 minus twice gm by r. I'm writing in a unit where the gravitational constant is 1. So given that, so what you do is you try to solve these equations with these conditions by taking different central energy density. You take so much energy density is at the center. Sure. And you try to integrate this equation from center to the surface. And the surface is defined by this. Okay? And using the relation between pressure and energy density. Okay? Pressure and energy density is the equation of state. So that is what, I mean, you can write a Runge-Kutta method of solving differential equation and can solve it. And this is how the neutron star mass will look like. It is a function of radius. Where it bends and it becomes unstable, that is the maximum mass which it has. So this is also this is for the pure neutron matter, and this is for the mixed phase, the quark matter core. Yeah, so this is, for example, if I calculate how does the energy density inside the star changes. So this is how it starts, for example, like this, it decreases. Here there is a phase transition, so there is this cake kind of structure. This starts with quark matter equation of state in the mixed phase, and then this goes like neutron matter equation of state. Whereas pressure is somewhat. So you don't have quark core? This is the quark core. Quark core is only in the mixed phase. Your pure quark metal core, it is not stable. It is beyond stability. At least in this model. Now, if I try to calculate the velocity of sound, this is derivative of pressure with respect to energy density, or the speed of sound. So as you see, as you come out of the core, it is about 0.2, and there is suddenly a jump at the phase transition, and then it vanishes. Whereas in neutron metal, it is a smooth form. Okay. Now, as I said, I mean this sudden jump in the velocity of sound has its consequences on the radial oscillations, and there are so these oscillations are classified something called pressure mode, fundamental mode, and gravity mode. These are very high frequency ones. This is the high frequency oscillation mode, and this is the lowest. It is few hundred hertz, and this is about few kilohertz, and this is about few hundred of kilohertz. So these are different modes of this thing, and you can actually calculate it by using the Einstein Equation. These are the so-called pulsation equation, and so these are you just little bit of perturb this by this function W and D, and you can write down the Einstein equation for this perturbation will give rise to change in the energy momentum tensor, and you write down the Euler equation of the Einstein equation. You will have these two equations satisfied by this perturbing function. Okay? As you know, as I mentioned, this perturbing function depends inversely upon the velocity of sound square. So if there is a change in velocity of sound, it will get reflected here. You expect it. Again, you try to solve it with some standard boundary value condition, continuity condition, and you can solve for this. Omega is the frequency here. As I said, this is the frequency here. So you have to essentially solve for omega. Okay. You solve for this omega. There can be multiple solutions, and different solutions omega correspond to different modes that I told you earlier. F mode, B mode, and P mode depend upon the different solutions of omega. There can be multiple solutions. Okay, and so this is again not so important. So these are the solutions of this differential equation. I won't tell much about it. So so if you have neutron stars, your nuclear matter, you get these frequencies in the range of kilohertz. That is what you have seen. And if there is a quark core, the maximum goes like this. There is little enhancement. So these are essentially the F mode, because it is in the kilohertz range. But if it is there is a quark core, there is a sudden change, you can have very low frequency modes, about few hundred hertz for the quark core. It is for the region where there is a quark core. So there is a change in velocity of sound, and that gives rise to low frequency gravity modes. Okay, these are called gravity modes in the context of atmospheric physics, atmospheric physics notation. Because the restoring force is essentially buoyancy. I won't go into detail of that. But the point is, this 200 hertz is apparently sensitive to the gravitational wave detector sensitivity. And so these are the conclusions. low frequency G mode occur for hybrid star, and which is due to sudden increase in speed of sound at the end of the base phase. So this is a very simple model we have done, but there are multiple generalization around different things. Yeah, so much to be explored. That's it. Thank you. Sorry?
Lagrange actually written some slides. Can you
From?
some
Lagrange. Uh-huh.
Can you derive it?
There is?
Can you derive it?
No, Lagrangian is take as an ansatz from which you can, that's your model part. Okay, you cannot derive a Lagrangian. Okay. Yeah, you can think of the physics and that will give you the Lagrangian. It is based on certain principles, like it should be a scalar, it should be a large invariant. So all these principles you do, there should be attractive part. How do I couple a scalar field to a Fermion field? Whether it should be if psi is a Fermion field, whether it should be psi bar psi phi or psi bar gamma phi psi phi, all these things will depend on what do you want, how do you model the interaction. So it's part of your input. It is not derived. It is taken on the as some kind of an ansatz. What Lagrangian would be. Okay. So for the depending upon the physics, as I said, I mean the basic thing I know about nuclear physics principle that nuclear matter has a saturation property, and how do I generate a saturation property from a Lagrangian relativistic formulation? That is true. That can be done appropriately choosing a scalar exchange or a vector exchange. Scalar exchange will give rise to attraction, vector exchange will give rise to repulsion. Okay, so you choose the coupling appropriately so that there is a minimum as a balance between this attractive and repulsive force. And at a density, this is the nuclear matter density. So you choose those couplings, you can tune it so that you get whatever the binding energy for nuclear at, I don't know how much it is, 16 and 14 MeV?
15 point.
Yeah, 15, of the order of 15 MeV at 0.16 nucleons per Fermi cube. So you choose your coupling such that is there. Then of course you try to modify it. It may not give rise to the correct compressibility of nuclear matter. So you try to figure out, let me add cubic or quartic term in the scalar field. Maybe it will reduce a little bit. Or you can have a cross coupling between the scalar and vector. Or you add a iso vector field that will distinguish between neutron and proton and the symmetry energy. So you try to model the Lagrangian so that the nuclear matter properties are reproducible. You choose it accordingly. Or at a fundamental level, on the other hand, there are certain principles like Gauge principle, which tell you at a fundamental level what is the QED Lagrangian or QCD Lagrangian or electroweak Lagrangian. So there are certain principles based on which you can write. You cannot derive it.
It's in classical
Some kind of. When you are talking about net value density, it's the number of variables minus RT values.
Number of variables minus RT.
At the time of beginning, its value is 0, and then it's positive. It's always positive.
No. Actually, for the Neutron Star case, when I said at zero temperature, the antivariant number is 0. So there is lot of, you have a star, there are, star is made up of, say, proton and electron like sun, and then if the mass is large enough, the electron and proton can fuse to make neutron, and neutron density will increase. And as he was telling, it can undergo a core collapse, and you will have a supernova, and after cooling it becomes a neutron star. So there the number density, if it is at somewhat zero temperature, it is only particles which contribute, not the antiparticle. So particle minus antiparticle number, that is positive. Okay, that's all.
So you mentioned the compact star and the hybrid star. What is it?
Yes, star, as I said, depending upon the mass of the star which is collapsing, like sun, like star, it can go to a, say, neutron star. Now, some of the neutron stars' densities can be large, so large that there is a phase transition possible to quark matter. And those stars which have a quark matter core and a neutron matter crust, those we call as hybrid star. It's just a notation. Neutron star with a quark matter core is called a hybrid star.
Compact star.
Yeah, these are called compact stars.
That is always compact.
And
Yeah.
sir, in page number 4 you mentioned the lambda, and there is also a lambda in between cosmology, which
This is different.
these are two different.
Yeah.
This
This lambda is the tidal deformability parameter.
and another question, sir. And I read that only higher masses stars go to the neutron star and lower mass star go to the dwarf planet. Why is it?
Yeah, the dynamics says so.
From the second.
So that's a GTR thing.
Thank you.
Okay, if there is no more questions, just thank Professor Mitra. We have 10 minutes break. Tea break.